Alright, ladies and gents, this is the video where I go over all the practice questions in the modern physics unit. I gave you 4 worksheets, well, 2 sheets, each with a double-sided, and so there should be 4 main topics to go over. And we start with the wave-particle duality nature of light. So light is both a particle and a wave. And we look at number 1 talking about light as a photon. So a photon of red light compared to a blue light. Okay. Blue light has what? So blue has higher frequency and shorter wavelength. So we can immediately cross off 2. We're not even talking about mass or speed. And it's definitely not lower frequency. It has to be greater energy, and why is that the case? For EM waves, frequency gives you energy. So high frequency, high energy. So blue is more intense than red in terms of energy. Number 2, exposure to ultraviolet radiation, UV rays versus visible light. So state one possible reason for this difference. UV has higher frequency and therefore higher energy. Alright, number 6, because we're skipping the 3, 4, 5. Wave-particle duality is most apparent in analyzing the motion of what? So baseball is just a particle. We can't see any wave nature. Space shuttle also acts as a single particle whose motion we could analyze that way, not in terms of waves. Galaxies is more like waves, like looking at black holes through gravitational waves, mapping it through such. But electrons is both a particle, but it can also have this wave nature to it. Alright, so it's an electron. Number 7, a photon of which electromagnetic radiation has the most energy. So we're looking for the one with the highest frequency. And so if you look at the spectrum on the reference table, microwave has low one, infrared is low. Now between ultraviolet and X-ray, X-ray has the highest, so it's choice 2, X-ray. Okay. Next, light of wavelength of that much consists of photons having what energy? So we're given a wavelength. So we got to use the energy equation hc over lambda. So E is equal to h, which is on the reference table, 6.63 to the negative 34 times 3e8 over 5e negative 7, you'll get that the answer is 4.0 times 10 to the negative 19 joules. That's choice 3. Number 9, electrons oscillating with the frequency of this produces electromagnetic waves. These waves would be classified as what? So we need to look at the reference table, look at the spectrum, just to see what kind of frequency, what kind of wave has that kind of frequency. So 10 to the 14th is definitely below visible light because they're all 10 to the 14th. Definitely not X-rays because that's above visible. So we're looking at either infrared and microwave. So a frequency of 10 to the 10th power would be somewhere in the microwave region. Okay, microwaves. 10. The energy of a photon is inversely proportional to what? So if energy goes up, what mystery quantity will go down when we say inversely? Well, energy happens to be directly related to frequency. So this mysterious quantity also has to be inversely proportional to wavelength. So if frequency goes up, so think of low frequency versus higher frequency. What do we also notice about these two waves? Low frequency has longer wavelength. High frequency has short wavelength. So it's inversely proportional to wavelength. Choice 1. Number 11, a photon has a wavelength of 9 times 10 to the negative 10. We need the energy. Again, is E equals hc over lambda. This is a 2-point question because we have to show work. So this is how you show your work. Don't forget units, joules, seconds, times 3 times 10 to the 8th meters per second over the wavelength, 9 times 10 to the negative 10 meters. you'll get 2.21 times 10 to the negative 16 joules. Alright, the next section we're going to talk about are energy levels. So this relies on using the reference table, energy level diagrams. So I'm going to try to pop in the diagram for you guys to look at for reference. Alright, so here is the energy level diagram, which you're going to need to use for a lot of these questions. Number 1 says, an electron in mercury atom drops from energy level I to the ground state by emitting a single photon of what energy? So we need to take the difference between I and ground state. So we look at this diagram for mercury. We look at energy level I, negative 1.56, and ground state is negative 10.38. How do we figure something out with these two numbers? You take the difference in their energy levels to figure out how much energy you need to go from this level to that level, and vice versa. So you take the initial energy level, subtract from the final energy level to figure out your answer. And that'll be, so negative 1.56 minus negative 10.38 electron volts. Take the difference and that'll equal 8.82. Number 3, the bright line emission spectrum of an element can best be explained by electrons transitioning between discrete energy levels in the atoms of that element. So discrete meaning specific. That's what discrete means. Has to be specific values. So if we look at this reference table, electrons cannot move up between or move down between energy levels unless you're either releasing or absorbing photons of the specific amount. Let's say you're going from ground state to n equals 2. If you go over the amount, you can't get there. You'll just fall back down. If you, well actually you don't even move at all. So if you absorb more than enough, you won't move at all. If you absorb under the amount, you won't move either. You only need to absorb the actual specific amount just to move between levels. And so this spectrum of colors that's being released as a result of them falling back down is determined by the energy. Energy you can convert to frequency. Frequency you can convert to the type of color. And so that's how we get the spectrum, based on the frequency, based on the energy of the photons. Okay, so that's tying in together the particle and the wave nature of light. Okay, so from the energy, you can get the frequency. From frequency, you can get the color. So that's how a spectrum is created. That's why certain elements give off different colors, because they have different energy level diagrams that show different values. Okay, number 4, explain why a hydrogen atom in the ground state can absorb 10.2 electron photon, but not this. So as I was going over before, 10.2 electron volts is the difference between n equals 1 and n equals 2, ground state to second level. That's the difference. That's why it could absorb it, because it can go from here to here. 11 is not the difference between the ground state and the third energy level. It's too little. It falls somewhere in between here. That's where 11 is. And so if you absorb not enough, falling anywhere in between, you won't move. That's why you can't absorb it. Number 5, excited hydrogen atoms are all in the n equals 3 state. How many different photon energies could possibly be emitted as these atoms return to ground state? So on the way down from n equals 3, it can fall down to n equals 2. That's one energy state. That's one energy it could give off. But also it gives off another energy going from 3 to 1. So it can emit two different types, going from 3 to 2, but also 3 to 1. Actually, I forgot one other thing. Not only can it go from 3 to 2 or 3 to 1, it could also go 2 to 1 on the way down. So after you go to 3 to 2, you could also go to 2 to 1. So that's 2 here and another third one over here. So there's 3 different energies it can release. The 3 to 1, 2 to 1, or 3 to 2. Okay. How much energy is required to move an electron in a mercury atom from the ground state to energy H? Okay, ground state to energy level H. So the difference between them, 10.38 minus 1.57. You should get 8.81. And that is right here, choice 2. Now I just had to move this to the other side so I can continue 7, 8, and 9, 10, and 11. All right, what is the energy in electron volts of the emitted photon going from n equals 3 to n equals 2? So the difference between the third and second energy levels for hydrogen, okay, 1.89 electron volts. Now we got to convert that electron volts to joules. So here's my phrase to remember, measured. You multiply going from electrons to joules, and that's what we're doing. We're going from electron volts to joules. The other way is joules to electron volts, you divide. Okay. So we're going to multiply by 1.6. So you multiply by that number, 1.89 times 1.6 times 10 to the negative 19 to get 3.024 times 10 to the negative 19 joules. Now we're going to use the joules to find the frequency with E equals HF. Okay. Don't forget to show units. Okay. Frequency will then be equal to what? Oop, I forgot to include here, the exponent is negative 34. So you should get a frequency of 4.56 times 10 to the 14th power hertz. Okay. Now we can figure out the wavelength. We could do it one of two ways. E equals hc over lambda, or what I'm going to prefer is V equals f lambda. Okay, we're using the speed of light in a vacuum. Times the wavelength. So it's 6.58 times 10 to the negative 7 meters. And that's correct. Okay. Number 11, a hydrogen atom with an electron initially in the second level is excited into the fourth level. This energy level change occurs because the atom has done what? When you go up, you absorb energy. When you go down, you release energy. Now the difference between the second and fourth, 4 is 0.85, second is 3.4. That looks to be about a margin of 2.55, choice 3. All right, on this page, we're only going to answer 5 questions. Number 2, the energy equivalent of 5 grams is what energy? So this is all E equals mc squared. So we're looking for E. Our mass is 0.005 kilograms. And C is the speed of light in a vacuum. Don't forget to square it. 4.5 times 10 to the 14th joules. Okay. Number 4, the energy equivalent of the rest mass of an electron is approximately what? So, mass of an electron, you have to look it up on the reference table. This I'll write for you because I have the reference table in front of me. The reference table says the mass of an electron is 9.11 times 10 to the negative 31 kilograms. So again, E equals mc squared to solve this question. Solving for E. you'll get 8.2 times 10 to the negative 14th joules, and that's choice 2. Number 5, the energy produced by the complete conversion of that many kilograms of mass into energy is what? Okay, again, this is E equals mc squared. (1.8 times 10 to the 12th power joules). So, tera or mega? Mega equals 10 to the 6th. Oops. Giga is 10 to the 9th. Tera is 10 to the 12th, so it is 1.8 terajoule. Okay. Number 10, what total mass must be converted into energy to produce a gamma photon with an energy of that many joules? Okay, so this time we're solving for m. It's a really small mass, 1.14 times 10 to the negative 30 kilograms, and that's choice 1. That's really small. Number 12, a uranium nucleus emits an alpha particle. New nucleus and alpha particle is less than the mass of the original. Explain what happens to the missing mass. So, if there's a loss of mass, what can mass do? It can convert to energy. So that's what happens, converts to energy. That's what E equals mc squared tells you, that mass and energy can be equivalent, can convert one to the other, convert mass to energy. So if you're missing some mass, some of it has gone into energy. That's all it is. Okay, the final topic is the standard model. Again, this is the reference table. We need to know about antiparticles, antimatter, the 4 fundamental forces, and how to use the reference table to answer questions about classification of matter and the standard model. Okay, number 1, the strong force. That's an important one to know by definition, and the strong force is what keeps the nucleus together. So it's attraction between protons and neutrons. So it's not repulsion, and it's not protons and electrons. That's wrong. So it's nucleons. Nucleons is another term for protons and neutrons. Okay. Number 2, the tau neutrino, the muon neutrino, and the electron neutrino are all what? So neutrinos are all found here. Where are they? They're leptons. So that's our answer to number 2. So choice 1. All right, number 3, a lambda particle consists of an up, a down, and a strange quark. So it's 3 quarks. 3 quarks makes a baryon. So that's our answer for number 3, because a lambda particle is classified as a baryon because it has 3 quarks. What is the charge of a lambda particle in elementary charges? So we have to look at the 3 quarks, up, down, and strange. Up is positive 2/3, down is negative 1/3, and so is a strange quark. So positive 2/3 minus 1/3 minus 1/3 equals 0 E. That's our answer, 0. It's neutral. All right. Proton is 2 ups, 1 down. Neutron is 1 up and 2 downs. A neutron decays into a proton. So going from neutron to proton, we go from UDD to UUD. So what is their conversion of? A D quark into an up quark. But that's not an answer. It's not choice 1. Is it a D quark into a meson? Is it a baryon to another baryon? Or is it a lepton to another lepton? Okay, it's definitely not a quark to a meson. So if we're going from neutron to proton, notice how they're both composed of 3 quarks. So if they're both 3 quarks, they're both baryons, so it's choice 3, a baryon to another baryon. Okay, number 6. Which is true of the strong nuclear force? The most obvious thing is that it holds protons and neutrons together, and that's the most essential thing. Okay, now we're moving on. All right, number 7. Which combination of quarks could produce a neutral baryon? So neutral meaning it's 0. The charge has to be 0. Baryon meaning 3 quarks. All 4 of our choices are 3 quarks each, so all we need to do is figure out the charges of each of them. Now I'm picking a color. Let's go with purple. All right, so what you do, you look at the reference table, look at the quarks, add up their charges, charm down and top. So there's 2 positive 2/3 minus 1/3 makes a positive 1. Charm top strange is also positive 1. Charm down bottom is 0, and charm down up is also positive 1, so it's only choice 3 that's the different one. So if you want to expand this, CDT comes out as positive 2/3 minus 1/3, positive 2/3. You look those charges up on the reference table right over here. That's what you need to do. Look these up and just add them up. If they talk about an anti-quark, then you look at these charges and do the opposite. That's what antiparticles do. For each particle, there's a corresponding antiparticle with a charge opposite. So up is positive 2/3, anti-up is negative 2/3. That's what they mean by antiparticle. All right, so we got number 7 out of the way, and now we're down to our final 2 questions. Ooh. Number 11. Protons and neutrons are examples of baryons. Beating a dead horse right here. Number 12. The force that holds protons and neutrons together is known as what? The strong force. Okay. Key thing, strong force is what holds the protons and neutrons together. What about that electron? Well, electron is right here. It's a lepton. Where's the electron located? Outside the nucleus. So that's why leptons don't experience this. Lepton's a no-no. Okay? That's the main thing to remember from the standard model. What is the strong force? And leptons do not experience the strong force. Alright. Hope that was helpful. Go through those practice questions. Go through the content review video that I'm going to send out along with this video link. Best of luck to all you guys studying. I know it's rough with everything compiling together at the last minute, but please, honestly, it's a quiz. Don't take it too seriously. There's a retake opportunity. Well, at the same time, you probably would want to take it seriously if you don't want to do a retake, so just try your best. I promise it won't be that difficult, unless you didn't study. It's very reference table based. Alright, that's it. Bye.